Okay, hey, so let's talk about these momentum problems. What a nice way to celebrate Christmas. So the first one, we have two carts. There's a spring. One cart gets pushed right, one cart gets pushed left. So we have a system, and there's a force this way on this cart. So there's a force this way on this cart. Hopefully that reminds you of one of our laws. Newton's third law. So another wording of Newton's third law is just that the momentum magnitude change on both objects is the same. So if the right one goes from 0 to mv, left one also goes from 0 to mv, but the direction's opposite. So this one goes this way with mv, and this one goes this way with mv. If v is positive, then this guy's going at negative mv. So B is the best answer for that question. This guy here, constant force, there's a time interval. What's the impulse? Well, we just got to figure out what impulse is, and impulse is delta P. We've defined impulse a couple times like this. Impulse is net force times time. Well, there's the net force, and there's the time. So, there's an equation that works. C. Now, similar, but a little bit different. This is the net force and time, good again, impulse of y. And the question is, what is the rate of change of momentum? Maybe you remember from class what this is, or we can just draw it out. The rate of change is momentum per time. A little bit of rearranging there, or our equation from a couple slides ago, delta P over T, that's the net force. So this question is just, what is the net force on the body? Easy. That didn't make sense. Pause it, watch it again. But this is just a way of describing net force, and they tell us what the net force is. This question, always tricky here, but let's make it a little bit easier for itself. Let's say this is 2 momentum units, goes into 2, and bounces off with 2. What's the momentum change? Is it 0 or is it 4? Well, this is plus 2. Let's imagine this is negative 2. So if we go from plus 2 to negative 2, is that a change of 0 or a change of 4? That's a change of 4. It's a vector. The direction matters here. So the momentum change here is actually PB plus PA. Net force is times time is the impulse. The net force is the impulse over time. So really we need to figure out the impulse on the object. If we can find this object's impulse, we can just divide it by time, because delta P, impulse, over T, that's the net force. All these questions have that very similar theme, didn't they? So now we have to ask, what is the momentum change? Well, it's PB to PA. I also like thinking of it as it starts at PB, it goes to 0, and then it goes to negative PA. That is a change of PA plus PB. The full change is PA plus PB. So that's why, nope, D is not the answer. It's this momentum change over time. So PB plus PA. This comes up a lot. Remember, the momentum is a vector. Right 2, left 2. Change is 4. Our favorite thinking graph. So some neat properties here. The area is the impulse. That's the change of momentum. For the entire trip from this point all the way to this point, velocity here is 0, the beginning, and the very end velocity is 0, which means all the areas together must all sum to be 0, because overall, the whole trip, there's no momentum change. All right, so then the initial part in the air, when they're leaving the ground, there's an upward impulse of 30. And we know at the very highest point, the velocity is 0 again. So then if initially there's an upward impulse of 30, but at this point there's no velocity, that means that there must be a downward impulse of 30 in this section here. This section must be down 30. So one more time, why must that be? Velocity here is 0. Velocity here is 0. And from there to there, then there's no overall impulse, no momentum change. But we're told the initial part has a momentum change of 30 up, must be a momentum change of 30 down. If the whole time is 2, this width here is 1. This area is 30. The height then must be 30 newtons. So the gravity force must be 30 newtons. So we can use that to figure out the mass. Maybe use 10, maybe use 9.8, but the main thing is the gravity force on the object must be 30. Zero velocity, it's going to be zero velocity here, zero velocity there, zero velocity there, but also somewhere else. Zero velocity is going to happen whenever the down areas sum up to equal the upward area. So we're kind of going along here, negative area, positive area, positive area. So whenever the negatives and the positives kind of balance out, then we get zero velocity. So maybe somewhere around here there's going to be a zero velocity, and then somewhere around probably here there'll be a zero velocity. That'll come up in the next question as well. So we had this graph here. The impulse was the net force over the time. Why was that helpful? I don't remember. But the P versus T graph, how are we going to do this? Well, maybe you set it up first by drawing some axes and you say, hey, graphs. I remember graphs, areas being useful, slopes being useful. What's the slope of a momentum time graph? It's the rise, delta P, over the run, change of time. That's net force. And look up here. This is the net force graph. So the slope of this graph is this graph. That's our trick. The slope of this graph is this graph. The slope of this graph is this graph. So maybe some 0 points are useful. All these points have zero net force. Remember, this means zero net force. So then all of these points have zero slope. So we're going to have to do our graph and get a zero slope at all these points here. There's also a few points where the velocity is zero, meaning the momentum is zero as well. Why is zero velocity helpful? Well, if the velocity is zero, of course, the momentum is zero as well. So we kind of have no momentum up to here somewhere. And then in this case, the net force is down. So the momentum will become down, or the slope of this graph has to match this graph. So we have a negative slope, zero. No, not zero slope. This, I can't undo. Oh, there we go. Oh, yeah, this is what we do. There we go. Yeah. So this thing here, and then negative, more negative, and then back to zero slope. Nope, that's not going to work either. 0, 0, 0, 0, negative, 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 negative. There we go. Zero slope. Whole time it's down, of course, because the net force is down. And then we have a positive slope, and eventually we get to a point where we're back to zero, the kind of our maximum momentum. And then we know the velocity here is zero. This is going to be a straight line because of the acceleration of gravity. And then we kind of land quickly, boom. And then it's up. And then, I'm messing things up. Oh yeah, positive slope. No, maximum, no, zero slope. I should have practiced this before I did this video. Okay, thank goodness there was a pause button on here. That took me another 10 minutes to draw this because I couldn't undo. I had to do one continuous mouse action, but there's the graph. It's probably better to talk to you in person about this. But something like that, my key thoughts were, I'm looking for areas where the net force graph is zero. So that's the blue line, so zero slope there. And then I kind of thought about what's happening to the person doing it. You can see even after 10 minutes of playing with this, I still managed to mess up the very last section of the graph. But that's the approximate shape. The tops and bottoms aren't great. Okay, that's already been a 9-minute video. Have a great day. Oh yeah, I have a last slide, don't I? I have like a goodbye slide. Good work slide. Good work. Not to me though, that was a horrible graph.